So here we have an optimization problem where a rectangle is bounded by the x-axis and the semicircle y equals the square root of 25 minus x squared. What length and width should the rectangle have so that its area is a maximum? All right, so this is an optimization problem because we are going to be optimizing the area in this problem. Specifically, we are trying to find the length and width of this rectangle such that its area is a maximum. And so in order to determine what the length and the width should be for this rectangle, in order to maximize its area, what we have to do is represent the area of this rectangle with an equation. And then we'll be able to use that equation to take a derivative and maximize the area. All right, and so how can we represent the area of this rectangle? Well, remember, the area of a rectangle is length times width, and in this case, we're going to want to represent the length and width using x and y. All right, this point right here on this graph represents the point that this rectangle would reach out to along the semicircle such that the area of that rectangle is a maximum. All right, and so how would we represent the area of that rectangle using x and y? Well, let's think about what x and y actually represent here. I know I said that it's a point along the semicircle that the rectangle reaches out to have a max area, but what do x and y look like on the actual rectangle? Well, x, or the x-coordinate of this point, represents the distance along the x-axis. So the distance from the y-axis right here to this point right here is x. So this right here is x. Half of the length of the rectangle would be represented by x, and then y, or the y-coordinate of this point, represents the height, or the distance from the x-axis to that point. All right, it's how far along the y-axis we are moving to get to that point. And so the width of the rectangle, or this distance right here, would be y. Okay, so now we can see that half of the length of the rectangle is x, and the width of the rectangle is y. So, if we want to represent the area of this rectangle in terms of x and y with an equation, and we know that the area of a rectangle is length times width, what would be the length times the width in terms of x and y? Well, let's write it down. The area would be equal to the length of the rectangle, which if half of it is x, then the entire length would be 2x, or 2 times x. So we'd have 2 times x, and then we're multiplying by the width, which is just y. All right, so we have 2x times y, and that will represent the area of this rectangle. That is going to be our primary equation for this optimization problem, the equation that represents the value that we are trying to optimize. Now, in order to actually maximize this area and find the values of x and y, and ultimately the length and width of the rectangle, what we have to do is take the derivative of this equation. But in order to do that, we need to express this equation, or express the area of the rectangle, in terms of just one variable. We don't want to work with an equation in terms of both x and y. We want an equation that is just in terms of x or just in terms of y. And so how can we do that in this case? Well, remember, we are given some other information in this problem. This rectangle that we are trying to maximize the area of needs to be inscribed within this semicircle. And that semicircle is represented by this equation, y equals the square root of 25 minus x squared. You can think of that as the constraint of this optimization problem. The constraint is always the equation that deals with some kind of a fixed value. In this case, the semicircle would be our quote-unquote fixed value because it's not going to change, right? We're not trying to maximize the area or the perimeter or anything like that about the semicircle. The semicircle is going to remain the same. It's constant. It is serving as a boundary for our rectangle. So this equation is our constraint, and we can use it to rewrite our primary equation, right? This equation tells us that y equals the square root of 25 minus x squared, so we can replace y in our area equation with the square root of 25 minus x squared, and that will give us an area equation entirely in terms of x, okay? And so if we do that, we'll have that the area is equal to 2 times x times the square root of 25 minus x squared. And that right there is the area equation in terms of one variable, specifically x, that we can use to optimize, or more specifically, maximize the area of this rectangle. All right, and we do that by taking the derivative of this equation. We'll take the derivative of it, set it equal to 0, and then solve for x, and that will give us the value of x for this equation that will maximize the area for the rectangle, which will help us determine the length and width of that rectangle with a maximum area. Now, before we do that though, something that we should think about, or something that we should write down, is the domain. Or in other words, what values of x would make sense in this problem, right? What is going to be the domain of x? Well, let's start by thinking about the smallest value that x could be. And so in order to determine that, we need to remember what x represents. X represents half of the length of the rectangle. And so theoretically, the smallest that x could be would be 0. What that would mean is that your rectangle would have no length and all width. So the value of y, or the width of the rectangle, would reach all the way up to the top of the semicircle. You just have a straight line and not really a rectangle, so there wouldn't really be any area there. So while 0 is technically the smallest value that x could be, it can't actually be 0. So it wouldn't make sense for x to be 0, but anything bigger than 0, up to a certain point, is going to make sense. So our lower bound will be 0, and we're not going to include it, so we have an open bracket, not a closed one. All right, we're not going to include 0 as our potential smallest value of x, but we are going to consider all values of x after 0. But where do we stop? What's going to be the largest value of x that would make sense in this problem? Well, if we think about it logically, we're going to be limited by the fact that this rectangle needs to stay inside of this semicircle. So what's the biggest half length that this rectangle could have? How far out from the y-axis could we measure half of that rectangle's length? Well, the semicircle reaches out to a value of 5 along the x-axis, and so it would make sense that a rectangle inside the semicircle is not going to go beyond that value of 5, right? If the value of x is half the length, then the biggest that could possibly be would be 5, the distance from the y-axis to the edge of the semicircle. Now, just like if x was equal to 0, if x is 5, in order to achieve that, y would have to be 0. The width of the rectangle would have to be nothing. You just have a straight line along the x-axis that goes from -5 to 5. And so it doesn't really make sense practically that x would be equal to 5, because then the width would be 0, and you wouldn't have a rectangle with any area. And so it makes sense for us to look at values of x up to 5. Anything less than 5, but still greater than 0, is going to make sense as a potential value of x that could maximize the area of the rectangle. I hope that makes sense. Our upper bound will be 5, but we're not going to include that either. Okay, so just to review, the domain of x, or the values of x that make sense for this problem, are any values between 0 and 5. Any value in between those two numbers is a possibility for a value of x that would give this rectangle a maximum area. Okay, so we want to keep this in mind, because when we take the derivative of this equation and set it equal to 0 and solve for x, if the value of x that we find is not within this domain, we can't use it. Okay, we need to make sure that that value of x we find makes sense. But now that we've determined that, let's go ahead and solve this optimization problem by taking the derivative of our primary equation and setting it equal to 0. All right, so let's take the derivative. We'll have a prime is equal to the derivative of 2x times the square root of 25 minus x squared. Before we take the derivative here, I think what we should do is first rewrite this square root to be this quantity to the 1/2 power. It's going to be easier for us to work with that. So I'm going to erase this square root right here, and I'm just going to rewrite it like this. We'll have 25 minus x squared to the 1/2 power. Remember that a square root and a 1/2 power are the same thing, but writing it in this way makes it easier for us to see how to take a derivative. And in order to take the derivative of 2x times this quantity, we are going to need to use the product rule, right? we have a product of two functions, or a product of two different parts involving x. We have 2x multiplied by this quantity to the 1/2 power. So, if you don't remember the product rule, I'll have it up here on the screen for you to reference, but it goes like this. We'll take the first function, which is 2x, and multiply by the derivative of the second function, and then add that to the second function multiplied by the derivative of the first function. But now let's focus on that first step. We're multiplying 2x times the derivative of the second function. Now, how do we take the derivative of 25 minus x squared to the 1/2 power? Well, that's going to involve the chain rule, right? We have a function within another function. Our inside function is 25 minus x squared, and our outside function is that quantity to the 1/2 power. So what we have to do via the chain rule is first take the derivative of the outside function, keeping that same inside function, and then multiplying by the derivative of that inside function. So that will look like this. The derivative of the outside function, we'll just use the power rule. We'll multiply that 1/2 down and subtract 1 from that power. So we will be multiplying by 1/2 times 25 minus x squared to the negative 1/2 power, right? We multiplied 1/2 down, kept the same inside function, and then subtracted 1 from the power, and 1/2 minus 1 is a negative 1/2. So that's the derivative of the outside function. Now we need to multiply by the derivative of the inside function, and the inside function is 25 minus x squared, and the derivative of 25 is 0 because 25 is a constant, and then the derivative of negative x squared will be negative 2x, right? We multiply the 2 down, so we have negative 2, and then you subtract 1 from the exponent, so you have 2 minus 1, which is 1. So you have negative 2x to the first power. Okay, so that's the first part of the product rule. Then we want to add that to our second function multiplied by the derivative of the first. So we're just going to have 25 minus x squared to the 1/2 power, and then we're multiplying by the derivative of 2x, and the derivative of 2x is just 2. We have x to the first power, so the derivative of that will be equal to its coefficient, which is 2. So I'll multiply by 2. And then that's the end of the product rule. So now let's simplify. We can make this derivative look a lot nicer before we set it equal to 0 and solve for x. The first thing I see is that we have 2x times 1/2. That 2 and this 1/2 will cancel each other out. 2 times 1/2 is 1. So I'm going to cross out 2 and 1/2. And then I see we have x and negative 2x. If we multiply those together, we'll have negative 2x squared. So a prime will be equal to negative 2x squared times 25 minus x squared to the negative 1/2 power. So I'll write that, 25 minus x squared to the negative 1/2 power. And then we're adding that to 2 times this quantity. So we'll have 2 times 25 minus x squared to the 1/2 power. Okay, now I'm going to rewrite this again, except now I'm going to rewrite these powers as square roots. 25 minus x squared to the negative 1/2 power will be the same as having the square root of 25 minus x squared in the denominator of this term, right? That negative power means that we can move this to the denominator to make the power positive, and then I'm just rewriting that 1/2 power as a square root. So this would be equal to negative 2x squared divided by the square root of 25 minus x squared, and then we're adding that to 2 times the square root of 25 minus x squared. All right, and so now that is our derivative. We don't need to simplify that any further. What we can do now is set it equal to 0 and solve for x. So let's work on that next. If we set our derivative equal to 0, we'll have 0 is equal to these same two terms. And now to solve for x, the first thing I'm going to do is add this expression to both sides of the equation. That will cancel out with this on this side and essentially just move it over to the other side, but it'll be positive instead of negative. So we'll have 2x squared divided by the square root of 25 minus x squared is equal to 2 times the square root of 25 minus x squared. Now the next thing that we can do is multiply both sides of the equation by the square root of 25 minus x squared. That will eliminate this square root from the denominator of this term, and we'll be multiplying the square root of a quantity by itself on this side of the equation, which will produce a very nice result. All right, and so here's what we're doing. We're multiplying both sides by the square root of 25 minus x squared. So I'll write that in here. On this side of the equation, multiplying by that square root will cancel out with the square root in the denominator. We have the same exact expression in the numerator and denominator, so they are going to cancel out. Anything divided by itself is 1, so we'll cross that out and cross that out. We're just going to be left with 2x squared on this side of the equation. And then over here, like I said, we have the square root of a quantity multiplied by itself, and whenever you have that, you're simply just going to have whatever is on the inside of that square root, right? For example, if you have the square root of 2 times the square root of 2, that's going to be equal to the square root of 4, because 2 times 2 is 4, and the square root of 4 is 2. So the square root of 2 times itself was just equal to 2, and in that same way, the square root of a value multiplied by the square root of that value is just going to give you that value. So this multiplication right here is just going to result in 25 minus x squared. All right, so here's how we'll rewrite this equation. This whole part right here will just become 25 minus x squared. And then on the other side of the equation, we're just going to be left with 2x squared. So I'll rewrite that and we'll have 2x squared. Okay, now we can simplify further in order to solve for x squared. If we divide both sides of the equation by 2, that will eliminate these 2's right here. So really, we could rewrite the equation again and just have x squared is equal to 25 minus x squared. And so if we add x squared to both sides of the equation, that will give us this equation. We'll have 2x squared is equal to 25. So now, if we divide both sides by 2, we'll have that x squared is equal to 25 divided by 2, and then we can solve for x by taking the square root of both sides of the equation. And so if we do that, that will give us that x is equal to plus or minus the square root of 25 divided by 2. And the square root of 25 is 5, so we could rewrite this to be 5 divided by the square root of 2. And if you wanted to, you could rationalize this answer by multiplying the numerator and denominator by the square root of 2. If you did that, if you multiply by the square root of 2 divided by itself, which is just a form of 1, you'll have 5 square roots of 2 in the numerator, and then the square root of 2 times the square root of 2 is just 2. So this answer would become 5 square roots of 2 divided by 2. All right, and we have 2 of those values, a positive version and a negative version, because we took the square root of both sides. All right, taking the square root of a value is going to give you a positive version and a negative version of that value. Okay, and now let's check to see what the actual value or the approximate value of this expression would be. If you plug this into your calculator, 5 square roots of 2 divided by 2, that is approximately equal to 3.54 and some more decimals. And so comparing that to our domain, if it's positive, it's within the domain, right? 3.54 is between 0 and 5. All right, at least when we're looking at that positive value of x. But if we look at the negative one, that would be negative 3.54, that would not be within our domain for x. So we can forget about that negative value and just focus on the positive x value of 5 square roots of 2 divided by 2. The other value, the negative one, is not within our domain. Okay, so we're just going to work with x equals 5 square roots of 2 divided by 2. That is going to be our value of x, or the value of half of the length of our rectangle that will give it the maximum area. Now we'll actually find the real length in just a second. First, let's find our value of y that corresponds to this value of x. And we can find that by plugging in what x is equal to into the constraint for what y is equal to. All right, so let's do that. We know that y is equal to the square root of 25 minus x squared, but we just found that x is equal to 5 square roots of 2 divided by 2. So we will have 5 square roots of 2 divided by 2 squared. And if you square that value, here's what we'll get. Y will be equal to the square root of 25 minus 25 times 2 divided by 4. right? 5 squared is 25, the square root of 2 squared is 2, and 2 squared is 4, and 25 times 2 is 50, and 50 divided by 4 would be reduced to 25 halves. So I can rewrite this to be 25 halves, and 25 minus 25 halves is just 25 halves. So we can rewrite this to be equal to the square root of 25 halves, which should look familiar. That's the exact same thing we found earlier for x. And so if we simplify further, you'll find that y is equal to 5 divided by the square root of 2, which if you rationalize that, will give you 5 square roots of 2 divided by 2. The same thing that we got for x. Okay, and so that's the value of y that corresponds to this value of x. That's going to give us the maximum area for this rectangle. But those are not our final answers, right? X and y are just the coordinates of this point for this rectangle such that it has a maximum area. But what is the actual length and width? Y would directly correspond to the width, but x is only half of the length of the rectangle. So while the width is just the value of y, it's 5 square roots of 2 divided by 2. That's the value of the width. The value of the length will be 2 times the value of x that we found. So 2 times 5 square roots of 2 divided by 2. If we multiply that by 2, we'll just be removing that 2 in the denominator, right? If I do this on the side here, 2 times 5 square roots of 2 divided by 2 would just be equal to 5 square roots of 2, because these 2's would cancel out, all right? And so 5 square roots of 2 will be the value of the length of the rectangle, such that it has a maximum area, of course. Okay, and so that would be the final answer to this optimization problem. If the length of this rectangle is 5 square roots of 2, and the width is 5 square roots of 2 divided by 2, then this rectangle will have the maximum possible area it can have, given that it needs to be within this semicircle and above the x-axis. Okay, and so with that, that is it for this optimization problem. If you have any questions, feel free to leave those in the comments. If you found this video to be helpful, feel free to check out some of my other calculus videos. I have a lot more videos on optimization, as well as other topics in Calculus 1 that you can check out. But with that, if you don't have any questions, this is all I had for now, so I will see you next time.